Hi, this is Lun Lam. Today is the third day of the AIRS in the Air Multirobot System lecture series. Thanks for joining us today. Likewise, today we are honored to have two distinguished scholars to share their latest research insights with us. Our first speaker is Professor Paolo Robuffo Giordano. He is a distinguished lecturer of the Technical Committee on the Multirobot Systems of the IEEE Robotics and Automation Society. And our second speaker is Professor David Navarro-Alarcon. I've known him for over 10 years since we pursued our PhD degrees at the Chinese University of Hong Kong. More information about the speakers will be provided by today's host, Dr. Yuan Gao. Dr. Gao is a research scientist with AIRS. He received his PhD degrees from the Uppsala University, and his research interest includes reinforcement learning and robotics. I hope that all of you will enjoy today's lectures. Without further delay, I would like to hand over to Dr. Gao. Dr. Gao, over to you.
All right. Hello, everyone. My name is Yuan Gao, and welcome to today's AIRS in the Air event. And as previously introduced by Professor Lam, that today we have two speakers, and Professor Paolo Robuffo Giordano is the first speaker, and he will be speaking about the control, state estimation, and the human interaction for multi-robot groups. Let's welcome Professor Paolo Robuffo Giordano for the first speech.
Thanks. Thank you very much. So I can share my slides. Yeah. Yes. Okay. Thank you. Just one moment. Okay. Does it work? Yeah. Okay. Okay. Perfect. So thank you very much for having invited me to this seminar. It's really a pleasure for me to participate and to share a little bit of what we have been doing over the years in multi-robots. So I have some introduction, because I don't know very well if the audience is very familiar with multi-robotics or not. So I prepared some generic slides at the beginning. I hope they can help the audience. So multi-robotics, we deal with coordination, information control, motion control, planning for multiple robot systems for many different kinds of tasks. So you can imagine like transportation, or for example, in warehouses when you want to ship goods around, or for exploration, for assembly. So sorry, there are many examples also. In research, these are some videos of some past results. It's a small collection, of course. If you Google around, you can find a lot of examples of what researchers have been doing in this field. For example, for cooperative transportation of rigid bodies, of deformable objects, formation control, in case of also by using many quadrotors, in this case, construction, okay? Exploration, human interaction, as we will see. So if you're interested in this field, I think it's a very exciting field, and you can really have fun. Now, coming to the more, let's say, scientific part. So, what is the main setting, the general we consider in research? Okay? So, you have this group of robots. They have some goal. The goal can be quite generic. It depends on the application. But for example, in general, it can be some kind of formation control. So, for example, reaching, maintaining some desired arrangement in space, or following a leader, or reaching a point of interest, covering an area, and so forth. And what makes in general the difference, especially for us in academia and research, is you want to develop algorithms that are able to also to cope with many limitations that these robots have. And these limitations, they come from what? In general, they come either from sensing. So it makes a big difference if you imagine that you have off-board or on-board sensing. Just to make a very simple example, imagine that you have a group of robots operating outdoors. Far from obstacle or obstructions. It's quite easy to reasonable to imagine that these robots can access GPS, and then with GPS they have a way of having, knowing where they are in a common frame without too much hassle, I will say. So this simplifies a lot also the algorithms. On the other hand, it's very different if the robots don't have access to this kind of external facilities or external measurement system, but they have to rely on their onboard sensings, for example, onboard cameras, lasers. Then this onboard sensing will have limitations. For example, cameras, they will have limited field of view, maximum range, occlusions, and so on. So they will have limitations, and the algorithms have to be able to cope also with these limitations. Okay? So this is the first motivation for a lot of research in, in multi-robotics. Then another big point is communication. So in general, when you have a group of robots, they need to share information over some radio signal in general. And then you want to try to limit the amount of information that the robots are exchanging between neighbors, but also you want to also limit in general how many neighbors every robot has in terms of communication. So you don't want to, in general, have communication structures like a complete graph where everyone is communicating with everyone else, because this increases a lot the communication load. But you would like to have some kind of more sparse graph when only some robots are communicating with other robots, but not with everyone. Okay? And then, of course, you have also issue about processing power. The robots that are used in multi-robotics are in general quite small or limited. They have limited payload and battery and autonomy, so they can only carry on board small processing units. So the computation that you want to do on board cannot be excessive. I mean, the algorithms that people developed should be easily implementable on limited hardware. All right, so yes, this summarizes a bit what I've said in this slide. So now, two main, I would say, basic problems in multi-robots, but which still motivate a lot of research today, especially again when people consider robots with onboard sensing and communication and no limitation that this implies, is formation control and localization. So now, for those who are not familiar with this word, what is formation control? So formation control is so let's start with localization. Maybe it's a bit easier. Maybe. So what is localization? Localization means in practice that every robot should be able to measure or reconstruct, estimate the relative pose of other robots in the group with respect to its own body frame. Okay? So this is a basic requirement if you want to control or to use or to plan your trajectory as a function of the trajectories or of the motion of the other robots in the group. You need to know where the other robots are with respect to yourself, at least the robots with whom you are interacting with. Okay? So localization is really a matter of knowing or estimating the relative poses by using whatever information you may have available. And the point is that in many cases, the information that the robots have available on board is limited. Again, if robots are using, for example, cameras on board, with a camera, you can get some information maybe about, I don't know, the bearing, the direction of another robot in your field of view, in your image plane, but you don't have access to the full pose of other robots in your body frame. And you may have occlusions, field of view, and so forth. So this is about localization. The other point is formation control. So formation control is, in a way, the dual problem, in the sense, let's say that you know where the other robots are. Now, the point is how you move and how the other robots should move, so that altogether we reach the spatial arrangement that we want to have. So either we reach some geometric shape, or we move altogether in a collective, with a collective behavior that we want. For example, like in flocking, we move altogether with a common velocity by maintaining some kind of limited spread and so forth. And so this is really about control. How we control the motion of one robot and the motion of the other robot, such that the geometric shape or goal that we want to have is realized. So typically, formation control. So for controlling, you need to know, you need to first solve the localization, in the sense that you need to know where the other robots are in order to control your own motion and the motion of the other robots. Okay, so I mean, this localization is an input for formation control. But there is also, I mean, one starts to think about it. There is also another, I mean, maybe a little more hidden link, in the sense that actually also formation control has an impact on localization. So this is kind of loop, which is also quite interesting to study from a research point of view. Why? because localization is an estimation problem. So you want to estimate, recover the state of another robot with respect to your frame with your own measurement. And it is a nonlinear estimation problem. And as in many nonlinear estimation problems, it is what matters is not only the measurement that you have, for example, the images from the camera, but also the motion that you are having. So you can have a motion, you can have a velocity, you can follow a trajectory, which, for example, makes it impossible to localize yourself or to localize the other robots. Because as an example, I don't know, if you're moving parallel to another robot, you're only measuring the distance with respect to the other robots, it is impossible, for example, to know the full state. So the motion has an impact on the localization. And then in fact, I mean, when you do formation control or when you control the motion, you should control it in such a way as to facilitate the task of the localization. So this is kind of, for those who are more into control theory, this is basically an observability problem, and you want to have a motion which maximizes the observability for localizing. So there is a nice loop here that, I mean, is interesting to study also from a research point of view. So now, coming to flying robots, I mean, multi-flying robots, of course, is a subset of multi-robotics. And when you have flying robots, you have the additional challenge that, of course, flying robots are a bit more complicated to control than ground robots, because they have to, I mean, they are more uncertain, and they also evolve in 3D, and especially when they fly in cluttered or obstacles populated spaces. I mean, with using onboard sensors, the safe flight can be problematic. I mean, somehow it's still a bit of a challenge today, even if a lot of advances have been made on this point. Anyway, in this context, basically what in general is a good idea, at least today, to do if you want to control multiple flying robots flying in a structured environment is to have some kind of layer with a local autonomy. Okay? And this local autonomy basically should take care about just flying and being stable while flying, but also by using onboard sensing, for example, vision for doing formation control, avoiding obstacles, solving low-level tasks. But then there is a higher level. So once we are able to keep a formation and to fly stably, what do we do? Okay, so the higher level. So how do we solve the mission that we have to accomplish? Where do we go? What is the next point to visit? And what area should we explore? So here, I mean, of course, you can try to do it also from the autonomy point of view, but I mean, in many cases, it makes sense to have a human operator in control of these higher level tasks. So the human operator decides basically what we do at higher level, and then the autonomy controls the low level details. Okay? And in this field, with our group, I mean, we made several contributions over the years, and also many other groups are working on this field. So it's a quite an interesting field, I think, about human multi-robot cooperation. And just to give you an idea of what we have been doing over the years, so I'll show some results. So, for example, this is one of the first attempts that we did in this kind of field. So what happens here is that I will play the video in a moment. I just explained. So there are 4 drones that have to keep a geometric shape, and this shape is a tetrahedron in this case. Okay. So the shape is maintained by the local autonomy, and there are also obstacles in the environment, and the obstacles are also avoided by the local autonomy. But the collective velocity of the group is decided by a human operator by acting on this force feedback device. This is like a joystick with force feedback. Okay? So the operator commands the collective velocity of the group, while the maintaining of the shape and the avoidance of the obstacle is done autonomously by the robots. And at the same time, the operator also receives a force feedback on the haptic device. Okay? And this would be the red arrow here. And this force feedback, basically, it's a force which is proportional to the difference between the velocity which is being commanded to the robots and the actual velocity of the robots. So what happens is that the operator is commanding the robots to move in this direction. There is an obstacle. The robots have to maneuver for avoiding this obstacle, and this maneuver is done autonomously by the robot. And while the robots are doing this maneuver, they slow down, and this is fed back to the operator as a force feedback. Okay? So the operator feels basically that the robots are slowing down, and it feels that there is an obstacle in the way, and then maybe he can keep pushing in that direction if he really wants to go in that direction, or he could maneuver around to avoid the obstacle. So this was one of the first attempts that we did, in this area of coupling the high-level commands of an operator with the autonomy of the group. Then we did also something similar. In this case, we were using cameras on board. Okay, this was, one of the early attempts. So you see, these colored balls on the drones are basically markers used by cameras for detecting the drones in the field of view in the image plane. You can see it here. And then basically here the drones are maintaining, since we are using cameras, they're maintaining the angles between the robots, because from the image plane you can easily get the direction, so the angle in 3D. And while they maintain a formation defined in terms of angles, the operator can move the formation as a whole while maintaining the angles between the robots. So this is another way of doing formation control with angles, bearings, in this case with the operator in control of the gross motion. So then another way of doing this coupling is saying that in some applications you may not have a rigid formation which must be kept by the robot. So like in the previous cases, but for example, every robot can move in a cluttered environment just by maintaining some kind of spring-like coupling between neighbors if these neighbors are in visibility. So if the robot is interacting with the neighbors, so you may have basically a graph which is time varying, because you can lose or gain neighbors as you move depending on visibility constraints or range constraints, basically on sensing constraints. Okay? And so in this video, basically what happens is that there is one robot, this one, which is the leader, if you want, which is controlled by the operator again. So the operator is controlling the velocity of this robot. And the other robots, they basically follow the leader or maintain a shape just because whenever they are interacting, so whenever they're in visibility, like a spring coupling is created among themselves. So when there is a blue link here, there is a spring between the robots, and then this spring keeps basically the robot all together, creates this cohesive behavior in the group, and the operator can, by steering the leader, can steer the whole group. And still with the force feedback, so the force feedback for the operator is again the difference between the commanded velocity and the actual velocity of the leader. And for example, if the leader starts losing robots in the group, then the operator will feel less inertia. If the leader has more robots in the group, the operator will feel more inertia. And if one robot in the group is dragged by an obstacle, the leader and then the operator will feel, the drag force to some extent. So it is a way again of informing the operator about something, what is going on to some level on the group. Okay. Now coming to a bit more algorithmic part. So in this video, I don't know if you paid attention. So this was at the time when we did it. A nice result, but there was a small issue, if you want, that maybe you may have noticed. So the small issue is that there is nothing that prevents the graph to become disconnected. Okay. So as the robots move around, for example, in this case, the leader is completely, at some point, it was completely disconnected from the group, because there was no action from the group to maintain connectivity of the graph. And of course, connectivity is a basic requirement that you must have for any cooperative behavior. So if the graph is not connected, it is not possible to share the information and to coordinate among the robots. Okay? So we started thinking about how we can do basically the same idea, but with the additional constraints that the graph must remain connected. So robots can still lose or gain neighbors as they move, but they can never violate connectivity of the graph. Okay? So now, for those who are more technically close to this field, this problem can be solved, in different ways, but one, I would say, natural way to address this problem is to consider basically a metric of connectivity of the graph. For those who are familiar with graph theory, you may know that a very famous matrix can be associated to a graph which is called the Laplacian matrix, and this Laplacian matrix, the eigenvalues of the Laplacian matrix, and in particular the second smallest eigenvalue of the Laplacian matrix, which is called lambda 2, is a measure of the connectivity of the graph, in the sense that if this second smallest eigenvalue is positive, the graph is connected. If it is 0, the graph is disconnected. This is a very well-known fact in graph theory that everyone knows about graphs. Okay? So this is basically this eigenvalue. So the point is that there is a matrix associated to a graph. You can compute the eigenvalues of this matrix, and one of these eigenvalues will be a good metric to quantify whether the graph is connected or not and how connected it is. So once you have this metric, this eigenvalue, basically I mean, at least at high level, you can imagine to have some kind of cost function, basically that grows to infinity, or in a way grows if the graph, if lambda 2 is approaching 0. So if the graph becomes disconnected, and then the robots, again, at high level, should try to minimize this cost function. So basically, every robot should be implementing some, for example, should follow the negative gradient of this cost function in order to minimize it and then keep lambda 2 larger than 0. And then, so this will be the action that preserves connectivity. And then you can imagine that in addition to this action, you can have additional tasks. So the control of every robot will be maintain the connectivity and do something else. And if the connectivity maintenance is strong enough, now loosely speaking, basically, and if this something else, this additional task is small enough in a sense, so the connectivity action can be proven to always win against any other possible action. And then this will mean that whatever action you're implementing in addition to the connectivity maintenance, the connectivity maintenance will always be able to maintain connectivity. So, and another point, just to give you a glimpse how these kind of works go. So basically, connectivity is so the presence or absence of an edge in the graph can be encoded by a weight on the edge that here I'm denoting with Aij. So this is a weight that can be 0 or 1, 0 if there is an edge, 0 if there is no edge, 1 if there is an edge. But these weights can also be made smooth in the sense you can imagine to have a weight on the edges, which is 1 if the edge is present, without any issue. But then if you have sensing constraints, for example, maximum range, you can imagine a weight that starts smoothly to approach 0 as the sensing constraint is reached. Okay? For example, if a maximum distance between the robots is reached, then the weight can smoothly go to 0. Okay? So these weights basically can be constructed in a very sophisticated way once you start playing with these ideas to encode sensing and communication constraints into the edges. For example, you can have a proximity sensing model, you can have a visibility sensing model where the weight is penalizing if an obstacle is entering the line of sight between two robots. You can also have a weight that tries to keep a desired distance among the robots and so forth. So now this video shows an implementation of all these ideas. So again, I just explained it before starting. So what happens in this video is that there are 4 robots, and 2 of them, the red one and the blue one, are controlled by 2 human operators. So this human operator is controlling the red robot, and this human operator is controlling the blue robot. Controlling means, again, commanding a velocity, and they can command whatever they want. So the red robot will follow the human A, and the blue robot will follow human B. The other 2 robots basically move only in order to keep the graph connected. Now, what happens here, for example, is that the blue robot, so human B, is commanding, human A is commanding the red robot to go in this direction. So now the red robot cannot really go in this direction, otherwise it will break this link. So what happens is that the robot autonomously slows down. The other robots, they do this kind of maneuver in order to let the red robot to move in this direction. And then as soon as this link can be created because these robots become visible, then this link can be lost and the red robot can now freely move in this direction. And during this whole time, the operator commanding the red robot was feeling again a force, and this force was basically proportional to the connectivity force. In the sense, this force was informing the operator that by moving in the direction that it was commanding, so this motion was going against the connectivity maintenance, and then it couldn't be really implemented. So this was again an easy way to inform the operator about, in this case, a much more abstract constraint, connectivity of the graph, directly on the degrees of freedom which are controlled by the operator. The operator just feels a force, and he knows that if he wants to move in this direction, this will be bad for the group. And being bad can again be a very simple and straightforward, can have a straightforward meaning, like I'm going against an obstacle, or can be a more abstract, like if I move in this direction, connectivity of the graph will be lost. So this is an easy way again to inform the operator about what's going on in the group. Okay, and then this connectivity action can also be extended to, for example, exploration in unknown environments. I go fast because I don't want to drag too much. Or more interestingly, the human multi-robot interaction can also be extended by using, for example, we did a lot of studies of what kind of feedback should be provided to the operator while controlling a group of multiple robots that need to keep connectivity. For example, in this case, we were using a bracelet here on the arm that was providing vibrations whenever the robot controlled by the operator was approaching the limits of connectivity. And in this case, the operator was actually moving together with the robots. So he was part of the group. He was just one agent of the group. But of course, the operator cannot be controlled because he's not a robot. Okay? And whenever the operator was moving away from the group or was threatening the connectivity of the group, he was feeling again a force on the two arms, informing him that by keeping moving in that direction, connectivity would have been lost, and by also informing about what direction should have moved for maintaining connectivity. Okay, so I think I have 5 minutes more, something like that, so I will try to go fast on this point. So another interesting problem that you may want to address in information control is that of rigidity. So now rigidity is maybe a bit less known than connectivity, but actually it's a very nice property of graph. So I cannot, of course, I don't have time to go into details because it's quite an interesting but also long topic. But it can be understood quite intuitively. So imagine that you have this graph. Okay? So this graph means you have 4 robots and they are maintaining distances over the edges. So this graph is not rigid because you can deform it without changing the distances over the edges. Okay? But if you add one edge, if you add one distance, one more, then now this graph is rigid because you cannot deform it in any way locally without changing the distances over the edges. Okay, so this is quite simple to understand. It's basically related also to rigidity of structures in civil engineering, for example. It's the same story. So now it happens that this very quite simple intuitive notion has a very important meaning for multi-robots. Why? Because if you want, it has to do, in my opinion, with so the main point is that of complexity reduction. So why? Because imagine now that you have many robots, not just 4, but in this case, I think 10 robots here. So it's easy to have a rigid formation if you consider the complete graph. If you consider that every robot is keeping a distance with respect to all the other robots in the group, then the graph will be rigid, all right? But the problem is that this will entail a quadratic complexity. So in order to do this, you need to control, estimate, measure, take care of a number of edges that, or distances or constraints that grows quadratically with the number of agents in the group. While you can be rigid, so you can obtain the same goal with a linear complexity. So, for example, if you are in the plane and you are considering distances, for the complete graph, you will need this number of edges for n robots. But it's possible to prove that you can be rigid, you can get away with just this number of edges as a function of the number of robots. And of course, as the number of robots increases, you see that this makes a big difference. I mean, here you will need to measure, control, treat, process 45 information compared to 17. And when it comes to measurement and to communication, this can make a difference. Okay? So now rigidity, why it is important to have a rigid graph? It is important for motion control and for localization. It is important for motion control because if the graph is rigid, then you can be ensured that if the robots are controlling the distances or the angles that they have with respect to the neighbors, then the shape that you want to reach will be reached. Okay? So it is like in this example. Since this graph is not rigid, so even if the robots are keeping the correct distances over the edges, you cannot be sure that the correct shape will be reached because you could be in this configuration or in this configuration. But with the rigid graph, if all the robots are keeping the distances over the edges, then you will know, you are ensured that also the shape is correct. Okay? So rigidity is important for motion control, but also for localization, because this is just a dual problem. In the sense now, if you are measuring distances or angles, and if you are rigid, you will be ensured that you can reconstruct where the poses of the robots in a common frame without ambiguity. So it's like the dual problem of formation control. Now, for rigidity, so basically there is when you move, you want to keep connectivity. In some applications, when you move, you may want to keep rigidity, because rigidity is a property that will facilitate formation control and localization. Okay? And then you basically get the problem of rigidity maintenance, like we had the problem before of connectivity maintenance. Now, for rigidity, it's a bit more involved, but likely one can can approach it as we did it for connectivity. So it is possible to build a matrix which is more involved than the Laplacian matrix, but anyway, it is possible to construct a matrix. Both eigenvalues will inform whether the graph is rigid or not. For example, for robots evolving in 3 dimensions and when considering distance constraints, it is very easy to show that by constructing the appropriate matrix, this matrix will have 6 eigenvalues in 0. This represents the null space motions of a rigid body in 3D, because a rigid body in 3D can translate in 3 directions and can rotate in 3 directions while being rigid. So there are 6 motions in the null space. And the 7th eigenvalue, if it is positive, this means that those are the only motions that are allowed, nothing more. So the shape cannot deform. Just intuitively, this is not how it goes. So anyway, the point here is that it is possible to build a matrix and to compute the eigenvalues of this matrix, and one of these eigenvalues can be taken as a metric of rigidity, like lambda 2 could be taken as a metric for connectivity. And then once one has a metric, again, like for the connectivity case, it is conceptually possible to imagine a cost function of this metric, and then the robot should minimize this cost function. I mean, this looks easy written like this. It's a bit much more involved, because the analytic expression of the gradient of this eigenvalue with respect to the robot positions is, not that straightforward, but it is possible to obtain it. No? And then, it's possible basically to implement a similar system like in the previous case for connectivity, where now the robots can still move around, can still lose or gain edges because of sensing constraints, but with the guarantee that the graph will remain rigid in this case, not only connected. And if the graph remains rigid, the robots are guaranteed to be able to locally localize themselves and also do formation control with only the onboard measurements that they have available. And just to conclude, it's also possible to, so what I've shown so far is about distance measurements. These are the typical measurements that you imagine on a robot. But actually, especially for quadrotors, in many cases, you have cameras on board, so more than distance sensors. Cameras are much more common, for sure, on quadrotors, and on drones in general. And cameras, you can imagine that you can extract a distance from images, but this is not that simple. You need a lot of assumptions or a lot of image processing. On the other hand, it's very, very easy to extract directions from image plane. Because on the image plane, if you are just able to segment the location of another drone in the image plane, then the pixel location of the image plane is basically a measurement of the 3D direction of that robot with respect to your body frame. So this 3D direction is also called bearing in the literature. So it's a 3D bearing if you're evolving in 3D. And this motivated in recent years a lot of research in how to do formation control, localization, rigidity for bearing formations, which means formations defined in terms of these 3D directions in 3D, if you're evolving in 3D. Again, why? Because these are what you can very easily obtained from onboard cameras. This is the main technological motivation. And we also did some work on this topic now without, again, going too much into details. This is the expression of a 3D bearing for a quadrotor in its body frame. And it's possible to take into account also limitations of cameras, like the field of view, occlusions, and so forth. Just to give an example, if, let me pause this video and then I start it again. So if now you have a formation which is defined in terms of these 3D bearings, these 3D angles, okay? And you want to be rigid, you still have some motions that you can do altogether while being rigid, Okay? Now, if you imagine every robot is keeping angles with respect to the neighbors, we can still all translate all together, okay? So these are motions that are possible when one is rigid with bearings. It is still possible to rotate all together around the vertical axis. And since we are only concerned with bearings which are angles, you get also an additional motion, which is scaling, because everything is up to a scale factor, of course, since these are just angles. So, and these are just examples of these motions. So these are motions that are not changing the angles of the, so are preserving rigidity and changing the angles between the robots, but yeah. So it's like for a rigid body, you can translate and rotate while the distances do not change, and for bearings, these are the motions that you can do without changing the angles for quadrotors. And it is also possible to define a bearing rigidity, a notion of rigidity for bearings, which basically goes very similar to what one do for the distance case. And it's possible, as I said, to also consider in the weight of the edges to consider sensing limitations typical of cameras, for example, minimum maximum range, limited field of view, even occlusions, okay? The fact that if a robot is passing in front of another robot, then the measurement with respect to this robot will be lost. And then, like for the distance case, it is possible to define a matrix, which is called the bearing rigidity matrix, whose eigenvalues will basically tell something about the rigidity of the graph. And then one of these eigenvalues can be taken as a metric for the rigidity, and one can implement a cost function on this eigenvalue, like what has been done, what we did for the distance case. And yes, this is an example of a formation which is, so in this case, every drone has a camera on board. These are the 4 camera views, and we are considering sensing constraints, which are limited field of view, range, but also occlusions. And the robots are, so one of the robots is moved by an operator, and the robots, they autonomously move and rotate in such a way as to keep the graph rigid in a bearing sense. And this allows them to recover their relative poses because the graph is rigid. So it's like a loop. It's like the loop that I told at the beginning of my talk when I said that localization goes into formation control, but formation control is a hidden loop that goes back into localization. Here, the motion keeps rigidity, and this allows for the localization to converge, which is then needed by the control. So it's this kind of loop. Okay, so this concludes my talk with my overview of the activities that we have been doing over these years. I mean, of course, for those who are interested in multi-robotics, I mean, you will also see what the other speakers will present. I mean, this world is very, very broad. Yeah? So I personally I come from a more control estimation background, so the contributions that I could give in this field are more in the control estimation part, but you have also a lot of people working in learning, in planning, in task allocation, so the multi-robot, in bio-inspired multi-robotics, so it's very, very broad. And it's very interesting because it has a lot of scientific challenges which still nowadays are unsolved if you really want to deploy multi-robots in real environments, not just in lab conditions. And also, for example, something that we are now starting to look into is the physical interaction. So cooperative transportation, manipulation with cables, for example, this is and with maybe a human operator who just drags an object that is transported by the robots with cables. So I mean, if you're interested in research, I think multi-robots is a nice field. So yes, this concludes my talk. Thank you very much for the attention.
Well, we thank Professor Giordano for this very interesting talk. I think it's a very interesting idea to have this idea of remaining connectivity and also the rigidity. It's a really very interesting topic. And we will enter the question and answering session. And I will have the first question. So I noticed that you have this way to adjust the connectivity in previous slide, and also seems that this parameter is related to like how fast can you go in a real system? Like what is your idea on this? Like what kind? I mean, if we increase the speed of the augment this kind of robots, and how robust is this method? Like, can it still remain connected, or what do you think of this?
Yes, so I think that so for the speed, I think that so the answer is a bit articulated, because in the sense, I mean, so let's talk about quadrotors, drones, okay? Because with ground robots the story is a bit different. But if we consider drones, quadrotors, so now you could go fast. Actually, I don't think that this will be an issue, because the point is that, so if you have a good flight controller that is able to track a reference velocity, then you can go fast, I think. I think that the main problem with quadrotors that we did not address is that we are imagining, so when we model these drones, these quadrotors for our multi-robot applications, we model them basically as a horizontal, so as a point that move on, how can I say, with, so we are not modeling the tilting and rolling of the drones, okay? For what concerns the control part. So this means that if you have a camera on board, for example, and if you start to go fast, for going fast or for braking, you have to tilt, of course. And if you tilt, then the camera on board or the sensor on board will be affected by this tilt. Okay? And we are not modeling this. So we are imagining that if there is a field of view constraint, you know, that the camera is always horizontal, and the field of view will not be rotated by the fact that the robot is braking or accelerating. So we are not modeling these effects, and this actually can be a problem, I have to say. We did not address it because I think it's not that easy to address, but it is an open point for me. I mean, I'm not aware of, I don't know, maybe someone addressed it, but I'm not aware of it. But so having a formation control, connectivity maintenance, which is explicitly able to take into account the fact that the quadrotors have these dynamics, and then this will affect the sensing constraints. So if you want to implement a connectivity maintenance, you have to know that you cannot break too. So this is an issue. So basically, in the videos that I showed, we are always in a regime where the drones are flying close to hovering, I would say, such that they don't fit too much. So otherwise, for me, it's an open point. Yeah.
Oh, okay. Yeah, thank you for the answer. And then let's see whether we have more questions here. Okay, I think it's incoming, maybe.
Excuse me, I have one question. The talk is very inspiring, and I'm curious about the oscillation problem, about the formation control. Have you ever encountered any oscillation problem when you are doing your experiment? Because the formation is actually a virtual linkage among them. When one robot moves, the other may can follow, but it will encounter some time delay or any control issue. Is there any things that we can do to tackle this problem?
Yeah. So let's say that. So I would say that oscillations because of delays, we did not have them. Why? Because since we are using onboard sensing, basically the fact that so yes, you could have a delay because if you have a camera on board, then the camera needs to process the images, and then but this delay in general is negligible compared to the dynamics. So the delay of measuring or processing the measurements is, in our cases, is negligible. So this kind of delay is, I would say, is not present. What is present is more that for anyone who has worked with multiple drones, these drones make a lot of wind. So when you start flying with several drones all together, they create a lot of aerodynamic disturbances between themselves. And then, yes, you can have oscillations because they are basically perturbing one with respect to each other. So now, this may seem as a very practical problem, and in a way it is. But actually, if you want to deploy multiple drones in, I don't know, for example, you see many times, you see papers or projects about, deploying multiple drones in, I don't know, collapsed buildings or, I don't know, obstacles and so forth. But if you start going to cluttered spaces, this becomes an issue because the drones, they make a lot of aerodynamic, I mean, they make a lot of wind to fly. And these, if they fly too close to structures or too close to each other, they quickly become unstable. So here again, we did something at some point in one of our previous works where basically we were penalizing the fact, so if one drone was flying like this, we were not allowing another drone to pass below, by means of some weight. So because if you have a drone passing under another drone, then the drone is completely destabilized. So you can imagine this kind of, the control will prevent that the drone passes under another drone. Or something else. So it's a bit heuristic, but yes, I would say that this is the main source of oscillations that I've seen in our context, not really the delay. Yeah.
All right. Thank you. Okay.
So let's see. Okay, I guess it's okay. Liang Guanqi asked, what are the challenges when there is limited connectivity among robots?
Yes, yeah. It's a very good question. So I see the question on the chat. So what is the problem? The problem is that the algorithms that people we implement for localization, formation control, or any higher level task, somehow, in most of the cases, they need to share information. So there is some information that needs to be shared among the robots. Okay? So for estimation purposes, for reaching consensus on some variables, and so forth. And of course, if the graph becomes disconnected, then it is impossible to share the information between the whole group, in the whole group. The group just become two separate groups. Yeah? So this is why you want to keep connectivity. Now, I have to say that I can agree, of course, that saying I want the graph to stay connected at all times can be a bit too conservative, in the sense that one could imagine situations in which at some point the group splits into two groups, they do something, and then they rejoin later on. That's completely possible, to imagine. But yes, I'd say that this requires a bit more complicated logic, because then if the two groups, they split, or they split in multiple groups, and there is no external entity that is coordinating the motion of the groups, then it's not that easy if you start thinking about it, how to implement policies that will guarantee you that at some point they will regain connectivity with the other group, if there are no external entities helping the subgroups to rejoin with each other. So this is why I think that in many works, people just say, let's keep the group connected so we can be sure that they will always be connected all together. And now I see that there is another comment, such are limited communication conditions field of view. Yes, so yeah, if the question was, yes, why at some point they lose edges, so maybe this was the question. So yes, basically they lose. So why they lose edges? Why one robot becomes disconnected with another robot? So because of either sensing or communication constraints. So if you need to sense, if a robot needs to measure, physically measure, for example, with an onboard camera, an onboard sensor, another robot, and at some point this other robot gets out of the field of view or out of the maximum range, out of the sensing constraints, then the measurement that the robot needed to take with respect to the other robot is not available anymore, and then the interaction edge is lost. In this sense, they are not interacting anymore. And the same goes with communication. communication in general is modeled as having, for example, maximum range. So you can imagine to be able to reliably send or receive information if another robot is not too far away. But if the robot gets too far away, then the signal becomes too weak and you are not able to reliably communicate any longer. And then you say, I lose the edge with respect to the other robots. These are the main reasons why, in practice, you lose neighbors, you gain neighbors because of sensing or communication constraints. I see there is another question. It is possible to upgrade the centralized controller multirobot system to distribute the controller system without losing decision-making and control effects. I think that in general, the answer is no, in the sense that, so I would say this, that the general answer is no. If you have a centralized solution and then you want to make it decentralized, you have to be ready to give up something, okay? In general. So give up something means, for example, give up convergence speed. You may still be able to reach the same accuracy or convergence goal but with more time, because now you need to wait the time that it takes for the information to spread over the group and come back and so forth. So it may take some more time, so you may give up time, but you may also need to give up optimality. So in some cases, it is not possible with a decentralized implementation to reach the same optimal configuration, or the same optimal decision, or the optimal control action as in a centralized case. So this is in the general situation. Now, there are some specific situations in which, no, it is possible to prove that also with the decentralized implementation, you have the same guarantees and the same performance of a centralized case. These are a bit lucky cases in which the structure of the problem is such that you can do this. But I have to say this is something that has to be seen case by case. And yes, there are a lot of people working on this general problem, which is also distributed optimization. If you have a special structure on the cost function, and then you can say something. But in general, I will say no. You have to give up something when you go from centralized to decentralized.
Okay, thanks again for the detailed answer. And due to the time limit, this may be the last question. And thanks again for Professor Paolo Robuffo Giordano. And
it was a pleasure.
we will continue with the next speaker.
Okay.
Yeah.
Bye-bye.
Right. So we will continue with the next speaker, Professor David Navarro-Alarcon. Professor David is with the Department of the Mechanical Engineering of the Hong Kong Polytechnic University, and he will be talking about multirobot systems. The topic is on shapes, robots, and sensor-based controls. Let's welcome Professor David Navarro-Alarcon.
Let me share my slides. All right, so I know I won't take too long. So thanks to the Artificial Intelligence and Robotics for Society, I got the number right for the invitation. I'm really surprised that I was, an honor, of course, that I was invited to give a talk on multi-agent systems, considering that, the mostly focus that I've done is in manipulation. So I was struggling and decided what sort of title I should use. And to combine the manipulation side with the recent multi-agent, multi-robot systems that my group is doing, I decided to come with this title, Shapes. I think shapes is one of the things that unites these areas of research. So yes, I'm David, I'm with the Hong Kong Polytechnic University. Really big thanks to my good friend, Professor Lam, who we both go, or our, history go a few years back. So look at it, we were quite young. 2011, this was AIRS 2011 in San Francisco with Juan Gao, everyone. And then he always had my back. So I really have to thank him. During 2019, he received us. We had a problem back then, and he led us, me and my group, to stay in his lab for a couple of months. So big thanks to him. All right, really quick, a bit about me. So I'm in Hong Kong, but I'm originally from Mexico. I came here, I've been here like since forever. 14 years this year will be. So I came here to study my PhD. I was trained under Professor Liu Yonghui in CUHK. And after I finished my PhD, almost 5 years, 5.5. I mean, nowadays it's a sin to spend more than 3. I was comfortably for 5 or so. I work afterwards as a researcher. I was a postdoc and I was an RAP with Professor Liu. I moved into PolyU, Li Gong Daxue, in 2017, and now as an independent PI, I received my very first batch of students in 2018, and I founded a laboratory. We call it the ROMI Lab, the Robotics and Machine Intelligence. We mostly do work on sensor-based control, both for any sort of robotic system, whether it's manipulation or something mobile. I was recently just start working as a service doing for IEEE TRO, where I'm now an associate editor. So yes, shapes. I love shapes. I don't know if you guys have seen this film, which I really like it. It was a 2016 Arrival. Really quick description, aliens arrive to Earth, humans go and see what's going on, and it turns out that these aliens only communicate through shapes. That's it. That was their language. No hi, no what's up, only these weird looking circular shapes. The interesting thing with this is that a lot of information is contained in this heptapod language. Actually, even some linguists have gone really deep into it, because it was originally designed by an academic linguist. So shapes have played a really important part in my research life, and I hold them dearly. So I mean, here I mentioned, so what is in a shape anyway? Beyond this sci-fi domain that Arrival took on encoding a language by these alien creatures. Geometric curves, if we go a little bit more technical, we can encode or embed information in them, just simply, geometric. We can have frequencies in them, configurations of for example, thinking of robots, changes, relative changes, aesthetics. I mean, some may like some droid. There are many things that we can encode and pour into some geometric curve, which can be extended, not just as a one-dimensional curve. It can be a surface, volume, in whatever dimensions you want to start going up. So this is the umbrella term on the work that I'm better go quick because I'm a bit late, that I'm presenting in this lovely afternoon is what do shapes have to do with robotics? Can we use them? How can we exploit shapes for robotics? There are 3 main areas that I'm presenting here today. One is under, of course, the theme of multi-robot systems. Yes, we can use shapes to guide manipulation. We can use shapes to represent formations, not as in position formations. There's no position, but as in a parametric formation with not an explicitly provided position. We can also use shapes to inform deformable agents that can adopt a different geometry. So with going with the first one, so this is a problem that I have worked for several years, and many students of mine are also happy to do it, which, I personally call it like shape surveying. It's a visual surveying, with the exception that the object or the main interest is centered on the geometry of a non-rigid object. So what does shape surveying is about? Well, we have a shape that we observe that comes from a non-rigid object, deformable object, and we want a robot, a multi-robot system, to deform it into a different configuration. That's, graphically what it means, and mathematically a very friendly description. Now, one of the core problems in this area And what we have been working very hard is, well, shape is just a word, a curve is a concept. So to use it in robots, you need to quantify, you need to measure it. How do you measure it? Here I present these two possible solutions. Well, you can either use all the information provided, for example, from a camera, which can lead you to a very large, let's call it a feature vector, 100, 200, 500 data points. Or, as I here propose with our team, is to develop a latent representation for it. So there are many recipes, numerical recipes, that provide you a compact representation. So we can formulate this shape servoing as a simple, well, not simple, as a well-known, friendly servo control problem, where we characterize with a compact vector of shapes, and then we provide a compact vector of a desired shape. All pretty standard. So how does it work? Well, what have we done? We use this compact characterization. We use Fourier series, truncated Fourier series. So we know Fourier series is an infinite series to truly approximate. The thing here is that, well, we don't have, I hear suggest we don't necessarily need to have it doesn't bring you much benefits if you have a very accurate representation. Simulation and control are two different problems. We're not simulating anything. We're just trying to control something in an efficient way. So we use a very compact approximation of this, typically using 4, 5 most harmonics, and the approximation is quite well. What we use as a characterization here are the Fourier coefficients. So shape for us here becomes coefficients. These constant coefficients for a given shape will represent for us the geometry of the object or the shape. So this is a video that I like showing because it's clearly depicts how things work. So we have a given desired shape, which we transform. So this is 2D points, not necessarily 2D, it could be, in an n-dimensional space, but here, simplicity, we use 2D. We transform this 2D point, which is the desired contour, we project it into, let's say, Fourier coefficient space, and then we do, simple servo control problem. And we can steer, if you use different terminology, the feedback shape into a target contour. This is it, a very basic idea. So we have implemented with many weird targets. For example, here we know we're not really going to reach it, but the robot will stop somewhere. We can still guide this configuration towards this target. We'll achieve what is local minima. So we have studied this, using very different approaches. We did this in collaboration with my friend Andrea Cherubini and his then student, a professor in New York, Drew G. Hom. And instead of using Fourier coefficients, we use, well, there's so many, as I put it, so many recipes that you can use. But all of them encapsulate this idea of obtaining a compact representation in order to make control efficient. So we perform very standard eigen decomposition, where we project all the very long, let's call it a contour, image contour data vector into a reduced space, reduced up to how many coordinates you want to have, how many representative coordinates you want to have. So we did this with a robot, which has 2 arms, but we don't, at least for this one, we're not using the other one. No, we are. Look at this, multi-robot. Check. I'm doing multi-robot here. So we deform the object towards a desired configuration. There's nothing that impedes you from using it for doing rigid bodies. The approach is just a description of shapes. We can do, this is a nice result, which involves both translation and then shaping of the object. We translate the spongy and then we bend it towards a desired target. So yeah, this one we worked with our French colleagues. More ways to encode multiple robots, 2N effectors, check. We did this in collaboration with HIT. We received a very hardworking, HIT people, I love them, very hardworking student. He visited us for, well, he was in Professor Lam's lab, actually. He visited us in 2019 and he stayed early 2020. And with him, we developed this different encoding of shapes for multi-robots that use contour moments. With only 10 numbers, you can get a pretty decent approximation of these shapes that objects, deformable objects have. And we can see how they vary as these two robots are doing manipulation. So all of that is the perception part. We can do automatic control. We can provide targets. We can bend objects towards the size shapes. We can unfold wallets. It also equally well works just for rigid objects. So this is some work that we did with HIT and ELF, also Jihong helped us here. And this was just published last year in TMEC. And more multi-robot, we've done. This is a multi-robot, 2 arms. We are doing packing of deformable linear objects. So the idea is let's transfer in an optimal way several types of objects into some container. I mean, motivation, there's several. There's so many now e-commerce companies. Everyone wants to have now products that you buy with your phone. And we have a lot of people still manually doing. How sustainable that is, I don't know. We're working, developing the enabling technology so that we can robotize this. Along the research directions that we do, we contributed in manipulating deformable bodies. This is what we do. So we use this multi-robot manipulator system to bend these objects into optimal shapes that will make this object fit into compact boxes. We did a very extensive study. We tested with, I think, how many, like more than 10 different objects with different lengths, different stiffness, and even different geometries. This work, we collaborate with Shanghai Jiaotong. My friend Wang Heshen also helped us and his students in doing this. We have so many results, I think. We can go through them. This, for example, this object is hollow. And here the key challenge is how to design the algorithm that can collaboratively manipulate, deform, and bend these objects into specific shapes that fit the box. Now, shapes unite us all. One shape to rule them all. We can also smoothly transition into, what is the simplest form of robot that we can possibly have, a good old two-wheel differential drive mobile agent. We have worked with an ongoing PhD student into doing formation control, some form of formation control. That here our intention is that we don't necessarily, we don't actually provide specific target positions to the robots. So we don't tell them this is the exact, let's say, Cartesian 2D coordinate or relative, you may say that is relative to your neighbor. What we provide as the target configuration is, as we did in this previous work, just a parametric curve. That's what we want. It's a sketch that you can do with your hand. So the algorithm, or here the challenge is design a method that can automatically distribute them along this contour. So we have here, we do some, it is some work we have right now as a preprint. We have worked with a visiting scholar that we have here, Jose Romero. It's really good in control. And he has helped us with the theory for this. We are using differential drive agents to remove there's one coordinate that you can't really, it's not a fully actuated system. We have position orientation, we only have 2 wheels. We play a small trick where we shift the control point, what we call of the agent, from one location into another, and we can transform that as a single integrator system. So of course, we will leave the orientation path as not entirely controllable, but in our work seems to work okay. So yeah, this is the proposed idea. We have a contour. We want to distribute them along the curve. Well, there's a comment. Question to you guys, do you think, oh, that's not for me, I guess. Do you think, what are the difference in connections between, oh, well, I'll address that later. So yes, yeah, so this is how it works. We have, well, good thing. I mean, as a supervisor, we come up with the theory, we do the mathematics, we analyze it, and we run simulations. For some reason, and everyone can attest that simulations always work. And they work quite nicely in a simulation, numerical simulation environment. We can do anything we want. When we turn into experiments and when the hardware experiments reproduce what you have developed in your numerical simulation study, that's a pretty good feeling. We have developed these results where the target that we're giving to these agents they're not points, it's just a single equation, a parametric equation. The method will automatically distribute them along this curve. And well, I'm not really, due to time, addressing the connectivity, but we have also done some analysis, and we are, as we can see in the result, we can also achieve a nice result for switching topologies and switching targets. Yes, this one. All right, more same platform. I have this also very good student, master student, Bowen. He's helping us to do all this integration. And along the theme that I bring for Unite this as shapes and curves, we are interested for this work on developing. There are two things. One is what I hear calling the invisible curves that some insects leave for guiding their friends. This enables them to, for example, find the way home, find the way towards some food source, doing foraging. And another one is the notion of sensor-guided control, which is a very key area in my group. The sensor part here comes from the artificial pheromone that we are trying to reproduce in our system. And the curves, well, the invisible curves that we don't really see it here, but the agents are finding a way to navigate. So we have done some work in this. I'm skipping all the simple, it's not so advanced mathematics, but just the result. This is the task. So agents have initially a home, and there's some location for the food source that the team of these agents don't know about. We just initialize everyone with a random walk, go and explore the wall, interact with it. And we have two types of pheromone trails that this system can leave. One is the red, is pointing towards where home is. The other one is green trail. It points towards where the food is. The only communication that these agents have is through these artificial pheromones. And we can, I'm not sure if it's very seeable through your schemes, but we can see that eventually all this system can, through time, move on all the food. We have a small green square and all the little dots stop. It becomes depleted in our experiments. More shapes. Shapes. How many times have I said shapes today? So this is a group of traditional rigid agents. Now, where this theme of shapes enter? Now, can we develop a wheeled robot that can achieve different shapes? Sure thing. I mean, conceivable is not so strange to think of. If we have this simple architecture to, let's call it locomotion units joined by something. Why? I mean, somebody say, why do you even bother? Well, first of all, I like shapes. Second of all, it can improve, for example, versatility. A single I'll call it point agent, doesn't have the same interactions, physical interaction capabilities as something like this one. We can then do transportation of objects, which is basically manipulation, but with mobile agents. This is work, very nice work that my student Luisa is leading. We did in collaboration with Trish from Imperial, where we have here some disclaimer. This is not two robots joined by something soft. That isn't the case. This connection in the middle is rigid. We have a special material inside that when we pass current, the metal that we have some metal inside melts and therefore transitions from rigid to compliant. That's why we have these thermal images there. Okay, so what do we gain by doing that? Well, look at this. If we have this is a completely rigid agent. We pass current, one segment, here we're playing with two different independent segments. One segment can bend, and therefore you can interact with an object, you can achieve different shapes, do a parametric curve formation if that's what you want to do. So it increases the type of things we can conduct with this system. For example, this one, well, students that have done really great work, Bailin and Xuan, we can manipulate object by deforming this agent into a curve configuration. We can transport them and do many things. This work by Luisa, she published it just now in RAL. So these are part of the capabilities that a traditional point rigid agent can't really bring. And that's one of the reasons why we are pushing in this direction. So where does the multi come? I only see one. Well, this is our goal. Consider a non-convex object, rigid object. Let's go simple, vanilla for now. If we have only, people have done it actually, but not with convex objects, by the way. If you only have a point agent doing like multi-agent manipulation of this body, a single point agent will not really have the same surface contact area as our proposed soft rigid agent, as our system can change its shape, its morphology, and conform to different sort of objects. We have done, we have the algorithm, the theory, we're trapped in it, and we've started doing some experiments for this work. And this one, I want to show this one because we work with Professor Lam in this, and it's also about agents. So everyone today wants to see agents. We built a robot city. Many happily living, well, not so happily because they are doing jobs for us humans. And this work has been also recently published by my student Hoyin, who's for some reason I forgot to put her photo here. We're doing task allocation. Task allocation, what is that? Well, we have this enjoyable video. We give a whole small city of robots a job, and we need to develop an algorithm such that they decide who they want to work with. Each of these robots has a different capabilities. Some of them are taller, some of them have manipulators, have grippers, some of them just only sense. So we develop the location algorithm so that these small teams can self-organize, do the task. For example, this little fella asks for help. We have a graph selection network to find the best candidate, and they assemble, find some objects. So all of this is, oh no, we have experiments. We do. I don't know how long this video is. How long? 2 minutes. 2 minutes. I don't have 2 minutes. Partnership, well, we explore different collaboration strategies, solo, subcontract, partnership. Oh yes, here it is, the real world. I suspect this will be, oh yeah, I remember this one. Look at this, even Li Hoi and my student even replicated the shape of the virtual agents, which probably made the work to be twice as slower as it could be if we just use something simpler. So what are we doing here? Well, allocation of the task, detecting a hot object. There's some modules that have infrared cameras, can detect the object and move it somewhere else. Yeah, I mean, well, these are some of the directions we're working. These are my concluding remarks. I do stress shapes do matter, and they're very useful in geometry in general. I mean, for robotics. So I don't know who in the background people watching this, but we by using and studying geometry, hardcore geometry, not hardcore, simple, just geometry in this most basic form is just simply lines and curves that you use with your pen. We can use them for doing many things. For example, guiding manipulation tasks, especially with non-rigid materials. We can use them for specifying paths, motions, formations of a team of agents. And as I show here, we can also use it to inform the type of shapes that a special type of rigid, soft agent can do. On a more technical side, which I don't present today and skip it, all of these are simply sensor-based control. We feed into our algorithm various types of feedback and guide the motion of a moving machine. And that's pretty all. I thank everyone. I thank all this work is done by this amazing group of people. I'm just a guy poking them so that they move faster. So I acknowledge the work that all these people have done, and I thank everyone who's might not be listening. So this is the end of my talk. Thanks.
Thank you for Professor David Navarro-Alarcon for this very interesting talk, and this about the shapes. All right, and I think multi-robot has a lot of definitions. Definitely the collaborative manipulators and also this multi-robot shape manipulation is related to the topic. And now we enter the question and answer session, and I will have the first question. So I noticed that for the shapes that you are manipulating, it seems that most of them are like 2D deformable shapes. Like, what is your idea on like getting the observation of the 3D deformable shapes? Like, I mean, is that difficult? I mean, what do you think about this? Like,
oh yes, I mean, coincidentally, because Paolo was just here a minute ago from a paper. I don't know if it's published, and probably I shouldn't say. It was under review, but I know some work in the same institute have done, for example, if I refer to this, yeah, I mean, something like this. Mathematically, we represent a curve as a 1D, say, for example, parametric curve. Can we extend that to other dimensions? How about, well, the simplest, if we go one dimension of, is a surface. You can have a 3D surface. How difficult it is? Not so much, to be frank. I mean, this unnamed team just did it using some depth camera, and instead of having a 1D parametrization, is a 2D surface parametrization. And they can there are two manipulators also. It's a multi-manipulator system. They jointly deform the object and shape it into some desired 3D surface. So it's definitely doable.
all right, and I also noticed that you used a lot of Fourier transform in like identifying the target shape of the deformable objects, right? Like, yes. What do you think of
this one? Yes, also for the mobile agents, we use Fourier.
Oh, yeah. So, like generally speaking, is there any like drawbacks of this method? Like, what do you think of this method? Can you give some comments on this Fourier-based method?
Drawbacks. Well, I mean, any method has drawbacks. So the ones that I personally encounter, if we compare, whether it's for this curve characterization of formations or manipulators, if we represented using these, it is certainly, given the number of harmonics that you use, will be the size of your characterization. But the main drawback that I see compared with eigendecomposition is by definition optimal. So optimal up to what you want to consider in your data. So the one drawback, probably the major that at least in my head comes, is that Fourier approximations of shapes and curves is not really optimal. I mean, as compared to, for example, singular value decomposition, PCA, that's very optimal in this case. But it requires some training. That's the problem.
Okay, but it's faster, or
it's quite fast, actually. I don't see, at least computationally, never experience any. I mean, to do this, you need to gather sample points all around your, say, data space, so that you have a reach enough and your projection into a subspace is sufficiently well informed. So you don't need to do this, I don't know, call it offline collection of data points. But it's not so bad. I mean, you still can do it. But computationally speaking, when you run it, it's quite all right. I mean, I don't see a problem.
I see. Thanks again for the answer. And let's see what are more questions in the Chinese channel. Miao Jiamiao asked, what feature of the control algorithm that make it suitable for shapes?
What feature of the control algorithm makes it suitable for shapes?
Yeah.
I think I skip it. No, I have it here. Yeah, this one will work. So, I mean, this is the answer goes along the theme of sensor-based control. Whatever is the modality that you're using, or the flavor of your measurements, you still need to transform it. You need to find a mapping between your, let's call it feature space, and your motion space. So I mean, from practical experience, what is a good selection for doing shape control is, I will say, one where you can analytically find this transformation. If you know what your feature space in whatever shape descriptor you're using, how that is related with your, say, actuation space or robot motion, that's generally good. Otherwise, you will need to numerically approximate that transformation. So, yeah.
I see. Okay, the second question from Luo Haobo is, does the multi-robot system in the last video use reinforcement learning to complete the task? I found that its actions have been simplified. For example, the action of grasping may be that it is caught even if it is touched. Does this training not take symmetry into account?
The last one says, I think it's this one.
Yeah. Does the multi-robot system in the last video use reinforcement learning?
No.
Okay.
You didn't use it, right? No. The main author is here, and she says he didn't. So. No.
Okay, I see. So yeah. Okay, so this one. Okay. Let's wait for more questions.
Yes, I have some questions. Yeah, if others still typing your questions in the chat board. First of all, congratulations for your promotion.
Thanks so much. You noticed it. You noticed it.
Yeah, I noticed it.
I put it. I don't know if I should put it. I mean, this will be recorded, right?
Yeah.
What if something happens and I'm not? And I'm telling the world, yes, I received my Jedi badge and something happened. Yes, I hope things don't go bad in 2 months.
Okay. And another thing is that I very appreciate you use the shape to connecting all your jobs together, from your shape manipulation to the multi-robot system. So this very genius idea. We have two questions that I would like to ask. The first one is about the shape manipulation. I saw that you have many ways to manipulate the object to deform the shape. And I noticed that it seems that you haven't used the twisting motion for deforming the object, right? If I'm correct.
Yes, you are very perceptive, yes.
Yeah, would you
look like a reviewer number 2 in my papers.
Yeah, do you have any comments about this? Why
No
you
comment. No.
try to use the
Well,
twisting?
it's yeah. If you I mean, if we go to, let's say, this work by Big Tom, this one. So twisting was in this 2D case. Simply put, it's easier to work just with images. If we do twisting, the object will go, off the assumed plane that we're observing. But I already committed to say that 3D is not difficult. So no, I mean, yeah, I guess it's probably got used to it. I would say, I mean, because technically it's doable. You use a depth camera and you can measure not just a 2D image, but potentially a point cloud of some connection. But we never used it. Twisting will involve, with the end effect of having more control input degrees of freedom, not just the position, and you're considering orientation, and that makes it a little bit more difficult from the control side here. I mean, the transformations will be bigger, but this it seems for those who, there are many people who are still, who are submitting papers on this, and sometimes they always try to replicate the same sort of results. I mean, this has been done. I mean, not saying don't reproduce it, but the same sort of experiment has been done. If someone wants to do different things, try twisting. I haven't seen it. I mean, at least something really dexterous doing twisting would be doable. Very similar methodology. I don't see analytically something too different. So, yeah.
All right, thank you for your answer. Another question, I think, is also quite challenging question. Yes, it is about the robot that can be configurable to change the shape. You have a video.
Yes, the last one, this one.
Yeah, yes, this one. Yeah, it is a very, very good idea to change the shape, use the heat to deform the rod in between two chassis. And later on, you use a example to do some manipulation, and you said that you have 3 points of contact when you manipulate some object.
This one.
This
one. Yes.
Yeah. So, is there any difference if we use 3 mobile robots instead of the one?
Yes. Actually, think of this. If you have only, I'm oversimplifying. My war right now is against the simple mobile robot. So I'm going to be very mean to them. So I'm going to call these mobile robots a point robot. A point can only exert linear force. I mean, conceivable, you can only push in one direction. A surface conforming robot can, additionally to pushing, you can also potentially introduce moment. So at least from, this is very fundamental from the mechanics, very basic mechanics. These two are, clearly the traditional point mobile robot doesn't have the same capabilities as one of these systems.
Yeah. But if there are more than one robot, that means there are
more money. My system only needs 3, whereas with more of these, you need 10. So, I mean, yes, of course, you increase the number, have so many, you say that they are perfectly well attached to these points, and therefore they do the same function. I mean, yeah, but control 20 robots, control 10, as opposed to, I don't know, let's say 3. So,
all right.
Simplicity, I will say.
Yeah.
And also, it's just a point. It doesn't have surface contact area.
Yeah. Okay. Thank you.
Thanks for the input from Professor Lam. And so due to the time limit, today we end this session, and we are honored to have these 2 great talks about the multi-robot systems. And I guess that's it. That is all. Thank you everyone for joining. Thank you everyone for your patience and participation. Yeah.
Thanks so much. Thanks.